Well, I'm going to make some anecdotal observations about stuff that happens at walls that are in contact with electrolyte solutions. And for the moment, I'm going to ask you to take these things as given. Later in the term, we'll actually go and show why these things are true and how we can prove that these things are true. But for the moment, I'll ask you to take them as given. And this information about the boundary conditions will then motivate a specific way that we're going to attack solving the Navier-Stokes equations. So I said, if I take a glass and I pour some water in it, and I take a very precise, small, perfect voltmeter, and I measure the voltage at the wall, and I measure the voltage in the bulk, I'll get that they're different. So one key thing that we know, or at least that I'm asserting, is that the voltage at a wall will be different from the voltage in the fluid. And the reason for this is that if these things are at equilibrium, the electrochemical potential has to be the same everywhere, but the chemical potential of an ion at a wall and an ion at the bulk aren't the same. So if the chemical potential of an ion on a wall and in the bulk aren't the same, then that means that their potential itself must be different for this to remain in equilibrium. And a simple way to think about that is that if I have a wall, say a glass wall, chemically the structure of a glass wall at a surface will be dominated by silanol groups. So it's a silane with an alcohol. And if I put pH 7 liquid, a pH 7 electrolyte solution in contact with this, these groups perform like weak acids. And so in the presence of pH 7 liquid, some of these protons will fall off. They'll go into solution as H plus ions or H3O plus ions. And what they'll leave is an SiO minus group. So we have a whole bunch of SiO minus groups. That will make the wall in aggregate negatively charged. And so there'll be a net negative charge density at the wall, and that will be associated with a relatively lower electrical potential at the wall. So from an equilibrium standpoint, I would say Gibbs free energy, electrochemical potential, to keep everything in equilibrium, this potential has to be different. Or you can also just think, well, if I take the water and I put it in contact, some of the protons are going to come off, and that will make this wall net negative charge. Now, if I take my magical thought voltmeter, I have one in the bulk and I have one next to the wall, and I measure a difference of, let's say, 80 millivolts, and I start moving this magical voltmeter away from the wall, I'll find I don't have to go very far for that voltage difference to go away. In fact, I have to go only about 10 nanometers. So the key conclusions are this wall that we will consider has a voltage that's different from the bulk, and that voltage difference decays in a very, very short length scale on the order of nanometers. So this is going to motivate us to analyze the system in a specific way. We're going to assume that the wall has a different potential. We're going to perform an integral boundary layer analysis of the flow near this wall. And the reason why we think we can do an integral boundary layer analysis is because all the action in this flow is so close to the wall. It's within 10 nanometers. I can just go 20, 30 nanometers away, and that's far enough for me to have integrated everything interesting. So I'm going to take a wall. I'm going to assume that I can describe the electrical potential of the system using a symbol phi, and I'll say somewhere in the bulk this phi is defined as 0. At the wall, and actually I need to use a different symbol here. So now I'm using just a script phi. At the wall, I'm going to say that the electrical potential is specified and given by a value phi naught. I'm going to assume that there's something interesting going on near the wall over a length scale that I don't quite know, but I'm going to assume that it's pretty small. And because it's pretty small, I'm going to consider a volume that looks like this, and I'm going to assume that in a relatively small distance from the wall, I can get far enough away that this electrical potential will be at a reference value that I define as 0. I'm going to consider flow parallel to this wall, and I'll apply the no-slip condition. And the question I now want to ask is, let's suppose I apply an electric field to this system that's parallel to this wall. I want to know what happens in the flow. Yeah?
Okay, if the charge on the wall depends on the structure of the wall, does it mean that the voltage difference that it would be measuring depend on the like if you in the plastic and in glass you measure two different
So yeah, so the question is, if the voltage at the wall is a function of the chemistry of the wall, does that mean that the voltage at the wall will be a function of the material? Yes. And does that mean that the resulting flow will be a function of the material? Yes. So if I take a tube and I make it out of plastic, I apply an electric field, I'll get flow and it'll have a specific velocity. If I make the same tube out of glass, that flow will have a different velocity. If I make the tube out of alumina instead of glass, the flow will go in the other direction. Everything is tied immediately to that chemistry. And furthermore, it means that if I have salty water at pH 7, I'll get one flow rate, and if I have salty water at pH 5, I'll get a different flow rate. So viscosity still affects this system as we would expect in all fluid mechanics, but now also all the chemical questions do. Other questions? Okay, I have a wall. I'm assuming this wall has a voltage that's different from the bulk, but that these voltage differences occur in a relatively small length scale. I'm not defining what that length scale is. It's just small enough that I argue that at some point I can get to this point where the potential has decayed to the bulk value. I'm going to apply an electric field parallel to this wall, and I'm going to use specific notation. I'm going to distinguish between two different electric fields. One, what I'll call the extrinsic electric field. And by extrinsic, I mean it's not intrinsic to the system. I applied it with I got a power supply. I took a power supply, I connected it to the wall, I connected some electrodes. I'm going to distinguish this extrinsic electric field moving in this x direction, from an intrinsic field that will exist in the y direction. Remember, I said there's a voltage difference between here and there, which means there has to be an electric field in this direction. I'm going to call that the intrinsic field because that's naturally coming from the chemistry of the system. It's not because I connected the power supply. And I'm going to use different symbols for these two things. The reason why I'm going to use different symbols is because the geometry of the system is simple enough that the intrinsic stuff is all in the y direction, the extrinsic is all in the x direction. They're different by something like 4 orders of magnitude, and so it's really easy to separate these things. It turns out you can still solve this problem without separating out this way, but doing it this way keeps the symbols straightforward. All right, well, we're going to assume that there's no pressure gradient. And we're going to assume that this flow is unidirectional. And in fact, these are the same assumptions that we made when we solved the Couette flow. But I'm no longer going to assume that the fluid is electroneutral. So anytime I write the Navier-Stokes equations and I don't have a rho E times E term, it's because I'm saying either it's not either it's electroneutral or there's no electric field. But I said I'm applying an electric field, and now I want you to no longer assume that the net charge density is 0. And because of that, I now have an extra term on the right-hand side. So now the governing equation I want to solve is given by this expression. Now what I'm saying is that in any local control volume, there's an electric field that's pushing on it, and that's being balanced out by a counteracting net flux of viscous momentum. All right. Now, this is where the stuff we did earlier in the class comes out. Actually, let me be a little bit more clear about my notation. I said I wanted to distinguish between the intrinsic and extrinsic electric fields. This rho e is going to be part of the intrinsic aspect of this. This is going to be a charge density that I'm finding in this area. It's being actuated in the x direction by this extrinsic electric field. And so I'm just going to add that subscript for clarity. Now, you'll recall that I said a critical thing that comes out of electrostatics is a relation between the charge density, which you'll see is not in my boundary conditions anywhere, and the electric field, or the potential, which isn't my boundary conditions. So I can't really do anything with this until I can connect it to the boundary conditions. And I'll do that by invoking Gauss's law. So Gauss's law says that the divergence of the electric displacement is given by the net charge density. I'm going to say that my electric displacement is given by epsilon times E. And I'm going to assume that epsilon is spatially uniform. And I'm also going to include the definition of the electric field, which is that the electric field is the negative gradient of the electrical potential. So this now lets me take the net charge density and relate it now to a spatial description of this potential. When I do that, I get this relation. So it basically says the volumetric viscous force is given by the Laplacian of the velocity, because I'm getting viscous fluxes associated with the gradients and I want to take that divergence. Here I have a Coulomb force, an electrostatic force, that's given by the permittivity and the electric field and the Laplacian of the electric potential. Why? Because if there's a Laplacian of the potential, there must have been charge there. That's what Gauss's law tells me. So in my mind, for what it's worth, maybe it's because I'm a fluid mechanician, like this makes sense to me directly. This makes sense to me directly. Like this, I have trouble understanding like what this means physically. When I see this, I always translate it back to this, which I understand. You, of course, need not be the same. The cool thing about this is in a simple geometry, a one-dimensional geometry. This is really easy to integrate. It's just as easy to integrate as the Couette flow was. So if I write this now in a one-dimensional form, if I assume that u is a function of y only, and I assume that the potential, this intrinsic potential, is a function of y only, I get that expression. Comments or questions? Yeah, cool.
There is an intrinsic electric field in the y direction. Does that exert a force on the fluid as well?
It does. So the question is, if there's an intrinsic electric field, does it also apply a force on the fluid? It does. So what we're doing right now is we're actually really, because I'm actually only writing u here, I'm solving Navier-Stokes equations with a forcing for the x momentum. We're doing that because it leads to the most interesting conclusion. This basically tells us how the flow moves in this system. If you take the same system and you apply, and the other thing about this is, even with very little information about the system, I actually can get the velocity answer here. Now, if I solve the Navier-Stokes equations in the y direction, what I get is that the pressure increases at the wall. I basically have a negatively charged wall. I have some positively charged ions nearby. There's a force pulling them together. That has to be balanced by a static pressure. And that, in fact, is the osmotic pressure of the electrical double layer. And we'll talk about those things. The problem with the y part, one, it doesn't drive the fluid flow at all. And the other thing is, to get anything meaningful about it, I have to solve for the spatial distribution of charge in the electrical double layer. Here, I don't need to know that yet. Here, I actually get the answer I want with a strictly integral boundary layer analysis. All I need to know are the boundary conditions, not the distribution of the potential. So you definitely can do it in the y direction. You get interesting and good stuff. But we're not quite ready for it yet, and it doesn't tell us about flow. It tells us about static pressure. Yeah, you had more questions.
When you wrote it as P there, as P intrinsic, is it like generally it should be like a general P rather than just intrinsic? For instance, if we have a non-uniform E external, then del square P would not necessarily be equal to del square P. Because that non-uniform electric field itself creates a del square P.
Right.
Would that have to be included?
Yeah, so generally, all the electric fields can be combined. So everything it's always electric field times, so for example, we took charge density rho E, and I turned that into a comment about the spatial distribution of the electric field. Technically speaking, that has to include everything. I'm splitting it up into intrinsic and extrinsic, not because I have to, but because I want you, when you see this E, to think of a driving force. And I want you to think of this in terms of the electric field acting on a test charge. When you see this, I want you to think that this is an indication of what the charge there actually was. And I want you to think of this as an expression of what a source charge does to an electric field. In terms of the math, neither of these subscripts are important. I really need to include everything. When I write that this is given by only the intrinsic, what I'm specifically assuming in this flow is I'm assuming the extrinsic field, either because of kinematics, has no specific contribution, or that its magnitude is small compared to the intrinsic field. And both are actually true. So there's no second derivative in, well, technically speaking, you can have a second derivative in a relevant direction. You don't for a couple reasons. One, the magnitude is very low, 4 orders of magnitude lower.
Because it's del dot D, so it's constant and that's
That's correct. So that is true if we make the assumption that the plate's flat, and if we assume that the electrical double layer is thin. And in general, those assumptions will be good. And in fact, we'll be making those assumptions for a chunk of the term. But it's also true that even if you make the geometry more complicated, usually the extrinsic field is orders of magnitude lower. So we have multiple different reasons why this is a good thing to neglect at the moment. Other comments or questions? Oh, you're saying rho E is given by this negative thing, and then I put in that value, and you're saying that my negative sign should go away? I believe you're correct. And in fact, I took it out over here, right? Yeah, so I'm pretty sure this is right, and we'll double check when we get the final answer. Yeah, Mukul.
External electric field, that would by itself create a space charge and
that's correct.
would drive that space charge itself?
That's correct. And that so examples of that would be that's not electro. So yeah. So the question is, will a non-uniform electric field drive a space charge, and then will it actuate that space charge? And the answer is yes. The simplest example of that is electrothermal flows, which don't have to be thermal in nature, but that's the name that gets used for it. So if I have a flow and I take a little dot in it and I make it hot, you find the conductivity goes up and the permittivity goes down. Because the conductivity goes up and the permittivity goes down, you find that the motion of charge in the system is no longer balanced, and it creates a localized space charge. That localized space charge is then acted on by that electric field. So the electric field both creates and then actuates a space charge. And so that sort of thing definitely happens. You'll find that those phenomena tend to dominate primarily when you use AC forcing. If you use a DC field, you see that all the linear stuff dominates. If you use AC forcing, then the nonlinear stuff dominates. And the creation of and then actuation of a space charge is inherently nonlinear, because the space charge you make is proportional to the electric field, and then the actuation is also proportional to the electric field. Okay, so I have this expression. I want to integrate it. I am super good at integrating easy expressions. So if I integrate this twice, I get this. We can show in a variety of different ways, in a variety of different geometries, that we can't have a velocity that becomes unbounded when the system becomes large. So this becomes 0. When I look at the y equal 0 case, so the case at the wall, I know what this velocity is. I know this velocity has to be 0 at the wall. And so if u is going to be 0 at the wall, this constant needs to be given by epsilon times the extrinsic field times this voltage at the wall. And I need this to be negative. So if I put these two constants in that come from the application of the boundary condition, I get this expression. Now, what does this tell me? It means that if I look at this flow, I have a velocity that's varying with y. It's varying with y specifically because I've written it as a function of the local potential, and this local potential is a function of y. I have not yet specified what phi of y is, but I have said that in this system, my local velocity is proportional to this local potential. When I go to the wall, when I go to y equals 0, where phi is equal to phi naught, this term cancels, and my velocity is 0, and that's consistent with the no-slip boundary condition that I specified. When I'm very far away from the wall, what's the value of phi? This is 0, right? So this goes away. And in the bulk, u is just given by minus epsilon phi naught times the extrinsic field divided by the viscosity. So if I have a wall that has some charge, and that charge is different from the bulk, I apply an extrinsic field parallel to this wall, I find that I get a velocity distribution that's varying as the potential varies. And I asserted that this potential actually varies from this value at the wall to the bulk value in a very, very short distance, like 10 nanometers. So if I have a 20 micron tube, this 10 nanometer film is so small that I'll never even notice it. So I actually don't care too much about what happens in this tiny thin little layer. I want to know what its effect is on the flow outside that little layer. And outside that layer, I have a uniform velocity. This velocity is proportional to the electric field I applied, so it's a linear system. It's proportional to the voltage difference at the wall, which means that whatever chemistry is driving this change in electrical potential, the flow I get is linearly proportional to that. And it's inversely proportional to the viscosity, because I'm pushing with Coulomb forces, and viscosity is the thing that's balancing that out. So I double the viscosity, everything's going to go slower. Now the way this looks physically, the spatial variation of this, again, we haven't shown what that is. I've done no derivation to determine what phi of y is, but I will tell you that roughly speaking, this electrical potential phi starts from its value at the wall. It decays as it goes to the bulk. One simple form of that can be an exponential decay, although it isn't always in that form. So if I plot the electrical potential phi on the y-axis as a function of y in the x-axis, so this graph here is y here, and then in this direction I'm plotting phi, I get a distribution that looks like this. This value here is phi is equal to 0. So as I go to the bulk, this phi is 0. I define that. It decays down to some value at the wall where phi is equal to phi naught. Again, I have not derived the fact that this decay is exponential or approximately exponential, but I'm hoping that you roll with me on this. We will, of course, derive that shortly. What does this tell us about the velocity distribution? If I tell you that this is what the potential distribution looks like, what does the velocity distribution look like? It basically looks the same as this. It turns out if I apply an electric field in this direction, I will get a velocity profile that looks just like this. Again, this distance over which this is changing, I've asserted that this is really small. I've asserted that this is like 10 nanometers. And so if I zoom in, or if I zoom out, and I just think, well, what if I have a tube, and what if its diameter is 20 microns, and I apply an electric field? If I graph out the velocity distribution in this tube, I will get something that looks like this. It will satisfy the no-slip condition at the wall, right here. But as we move away from the wall, it will accelerate to this bulk velocity, given by this expression, over this very short distance. If I look at this flow, if I measure this flow with a light microscope, right, if I put some particles in and I see how the particles move, or I use some other technique to measure the velocity of the flow, I'll never even see this part. 10 nanometers, way too small. I mean, technically speaking, you can see it, but not with just routine light microscopy. So basically what this means is that if I go into the lab and I take a tube and I put some stuff in it, an electrolyte solution, I apply an electric field and I see how the fluid moves, what I just see is a uniform velocity. Everything's moving at this velocity.